This morning I'm going to be going through assessment number 5 prep questions regarding conservation of energy. And so I'm just going to go through and answer each question and explain how I reason out what the answer is. So here I am, one of 19 problems. The actual assessment 5 has 30 problems on it, but these are the relevant problems that I could find. Anyway, here we go with number 1. Person X pushes twice as hard against the stationary brick wall as person Y. Which of the following statements is correct? Well, first of all, I'm not going to read all these statements out. I'm just going to think about what was just said there. Both of these persons, X and Y, they exert a force on the wall, but the wall doesn't move. And then it's going to ask me a question about work. Well, the fact is that in order for work to be done, there must be a displacement. So it's absolutely true that both of these people, X and Y, do no work. I don't have to read any of the other ones, but they're quite absurd. They all say they do work, they do work, they do work, and they do no work, because work is the parallel component of the force multiplied by the displacement. If there's no displacement, then there's no work done. Number 2, a 35 Newton bucket of water is lifted vertically 3 meters and then returned to its original position. How much work did gravity do on the bucket in this process? So the work done by gravity is the gravitational potential energy. So when I lift the bucket 3 meters, the work done by gravity is mgh, and it's negative, because as I lift the bucket upward, the force of gravity is downward, and so gravity is doing negative work. When I lower the bucket down again, the work done by gravity is mgh. I can ignore everything that happens in between. The work done by gravity is going to be mg multiplied by the change in height of the object. And this object does not change height. It has the same gravitational potential energy when it starts as when it finishes. Therefore, the work done by gravity is equal to 0. Gravity does the same amount of negative work on the way up as it does positive work on the way down, and the net result is 0. You throw a basketball, or a baseball rather, you throw a baseball straight up. Compare the sign of the work done while the ball goes up with the sign of the work done as it goes down. This relates to the previous question. If I draw a free body diagram for the baseball when it's on its way up, the force of gravity is directed downward, but the displacement is upward. When the force and the displacement are in opposite directions, this is when negative work is done. So the work is negative on the way up. So one of these second two choices is what I'm looking for. When the ball is falling downward, the force of gravity is downward and the displacement is downward. So I would expect the work to be positive on the way down, which is what makes this the correct solution. Which one has a larger kinetic energy? A 500 kilogram object moving at 40 meters per second or a 1,000 kilogram object moving at 20 meters per second? Well, we simply have to calculate the kinetic energies in order to tell. But if we're a little bit clever, we can do better than that, because this is a 5 kilogram object and a 1,000 kilogram object, which means the second object is twice as massive. But the second object is only going half the speed. You say, well, those two things cancel out, you see, so they'll be the same. Because kinetic energy is 1/2 mv squared. It depends on the square of the velocity, which means this faster speed means more. In fact, being double the speed means 4 times the kinetic energy. So if the 40 meters per second gives it 4 times and the mass only gives it half, then it's twice as large, and the 500 kilogram object has the larger kinetic energy because the speed matters more. A 4 kilogram object moving with a speed of 2 meters per second, a 1 kilogram object moving with a speed of 4 meters per second. Both objects encounter the same constant braking force when brought to rest. Which object travels the greater distance? Now, a key thing here is they experience the same force. In order to stop an object, you have to remove its kinetic energy, which means you have to do an amount of work that is equal to the kinetic energy. These two objects have different kinetic energies. We can tell which one has more because, well, do they? Do they actually? So it's 1/2 of 4 times 2 squared is 2 times 4 is 8. And the second one is 1 kilogram times 4 squared is 16. So it's, well, half of 16 is 8. So they both have the same kinetic energy. Which object travels the greater distance? They travel the same distance. They have the same initial kinetic energy and therefore travel the same distance when being brought to rest by a constant force. Well, I almost messed that one up. This is the work energy theorem. The change in kinetic energy is equal to the work done. Question 6. You and your friend, who weighs the same as you, want to go to the top of the Eiffel Tower. Your friend takes the elevator straight up and you decide to walk the spiral stairway, taking longer to do so. Compare the gravitational potential energy of you and your friend after you both reach the top. Here's the thing. Gravitational potential energy is mgh, the mass times g times the height to which you ascend. It does not matter how you get there. Now, it's true your friend went faster, and so that matters to power, as we'll see in a later question. But gravitational potential energy is mgh. You both have the same amount of gravitational potential energy at the top because you have the same mass, you're on the same planet, and you ascended to the same height. When you drop a pebble from a height h, it reaches the ground with kinetic energy k if there's no air resistance. From what height should you drop it so that you reach the ground with twice as much kinetic energy? I think this is one that's trying to catch students on guessing about square roots and proportionality and whatnot, because it's true that from time to time we encounter questions that are a little bit tricky because of square roots involved. But if I write the law of conservation of energy for this situation, the gravitational potential energy, mgh, that it has at the top is equal to the kinetic energy that it has at the end. So if I drop it with twice the gravitational potential energy, it's going to have twice the kinetic energy at the end. So the answer is I have to drop it from twice as high. If I drop it from twice as high, then it starts with twice the gravitational potential energy, and therefore will have twice the kinetic energy when it reaches the bottom. Two cyclists weigh the same and have identical bicycles ride up the same mountain, both starting at the same time. Joe rides straight up the mountain. Bob rides up a longer road that has a lower grade. Joe gets to the top before Bob. Ignoring friction and wind resistance, which one of the statements is true? This time I'm going to read through all the statements. Bob and Joe exerted the same amount of work, and the average power of each cyclist was also the same. It is true that they did the same amount of work because their gravitational potential energies increased by the same amount. So they did do the same amount of work. But Joe did the work faster, so Joe is more powerful. So this first one is not correct. The average power exerted by Bob and Joe were the same. Well, I just said the powers aren't the same. The amount of work done by Joe is equal to the amount of work done by Bob, but the average power exerted by Joe is greater than Bob. Joe is more powerful because he did the work faster. So that one is the correct answer. The last one is the reverse, saying that Bob is more powerful. He did the work slower. He's not the more powerful. A force produces power P by doing work W in time T. What power will be produced by a force 6 times as much in half the time? Well, power is going to be the work divided by the time. So if I have 6 times as much work, that's a 6 in the numerator. In half the time, that's a 1/2 in the denominator. Well, a 1/2 in the denominator is as good as a 2 in the numerator. That's 12 times the power. It did more work in less time. That's 12 times more powerful. You and a friend each carry a 15-kilogram suitcase up 2 flights of stairs walking at constant speed. Take each suitcase to be the system. Suppose you carry your suitcase up the stairs in 30 seconds while your friend takes 60 seconds. You did the same amount of work, but you are more powerful. And that's pretty much a repeat of the previous question. I think there are a few repeats in here, but it doesn't hurt to hit an idea twice. If you raise an object to a greater height, you are increasing its Potential energy. The rest of these are ridiculous answers. Heat, chemical energy, kinetic energy. No. There are some questions in homework. For example, you take a book that has no kinetic energy, put it up on a shelf, and then it has no kinetic energy. Sure, it had kinetic energy in the middle, but energy is all about initial and final. And so I'm raising its potential energy. Number 12. The unit of work is the joule. Whenever I'm working out units, sometimes it's useful to think about the equation involved. For example, sure, the work of the unit of work is joule, but if I want to think about it in SI units, I might think of, for example, kinetic energy, 1/2 mv squared. The mass is in kilograms, and the speed is in meters per second, but it's squared, which is meters squared per second squared. So I might also have a question where I say the unit of work, or the unit of energy, is the kilogram meters squared per second squared in SI units. Which has a larger kinetic energy, a 12-gram bullet fired at 550 meters per second, or a 10-kilogram bowling ball rolled at 11 meters per second? Oh, obviously, the bullet, right? Well, we have to do the calculation. Don't forget to convert grams to kilograms at 550 meters per second, or a bowling ball at 11 meters per second. So 1/2 mv squared for each. You'll discover that it's actually the bullet that has more kinetic energy, which is part of the reason why bullets are more dangerous than bowling balls, although bowling balls are much easier to dodge. A lightweight object and a very heavy object are sliding with equal speeds along a level frictionless surface. They both slide up the same frictionless hill with no air resistance. Which rises to the greater height? I don't know, you might call this a trick question, because they both have kinetic energy, but since they have equal speeds and different masses, they don't have the same kinetic energy. They have different kinetic energies. And then they both slide up the same frictional hill, no air resistance, which rises to a greater height. You feel almost certain that they must go to different heights. But the fact of the matter is they go to exactly the same height. And the reason for that, you know what, I was going to provide an equation, so I'm going to pause recording for just a second. Man, that was slick. Here's my equation. 1/2 mv squared is equal to mgh. They both have kinetic energy, but the kinetic energies are different. When they slide up the hill, they'll both have gravitational potential energy, and the gravitational potential energies are different. But when I write it as an issue of conservation of energy, the initial energy equal to the final energy, notice that the mass cancels in the equation. So if I were to solve for the final height in each case, it would be the speed squared divided by 2g, and both objects have the same speed, and therefore they slide to exactly the same height. Number 15, you hold a heavy weight over your head. The work you do is 0. Immediately I say 0, because work done is a force multiplied by a displacement. And if I'm just holding the weight over my head, the displacement is equal to 0, and therefore I do no work. 3 cars, F, G, and H, are moving with the same speed and slam on the brakes. The most massive car is F, and the least massive car is H. If the tires of all 3 cars have identical coefficients of friction with the road surface, which car travels the longest distance to skid to a stop? Now, previously in this assignment, we had a situation where masses had the same kinetic energy and they were subject to the same force and they traveled the same distance when stopping. Pardon me. They didn't travel the same distance when stopping. I'm confusing the issue there. Here, I'm going to look at this in order to suss this out. I'm going to look at this again in the context of conservation of energy, because I have these 3 cars and they all have different masses. F is the most massive and H is the least massive, but they're moving with the same speed. Same speed. They slam on the brakes. They have the same coefficients of friction. And how far are they going to skid to stop? The answer becomes obvious when I write the law of conservation of energy for it. They start with kinetic energy. Negative work is done by friction. Now here, the work done by friction is negative. The force of friction, which is mu mg, multiplied by the displacement delta x, is equal to 0. Notice in this equation, once again, just like the equation with the ramp, the masses cancel, making the solution to this problem, how far do they skid when coming to a stop, independent of mass. So the fact that F, G, and H all have different masses is a distractor. They all travel the same distance when stopping. When you throw a pebble straight up with initial speed v, it reaches a maximum height h with no air resistance. At what speed should you throw it up vertically so it'll go twice as high? Oh, I know, twice as fast. Hang on. The last time we encountered this question, we were dropping a thing from a height and asking about the kinetic energy at the end. Here it's talking about speed. In the kinetic energy equation, the speed is squared. So if I want to go twice as high, I want to increase my speed by a factor of square root of 2, so that when I square it, I get a factor of 2. So you want to be careful when you're talking about doubling the kinetic energy or doubling the speed, because the answers are different accordingly. A heavy sled and a light sled, both moving horizontally with the same speed, suddenly slide onto a rough patch of snow and eventually come to a stop. The coefficient of friction between the sleds and the snow is rough for both of them. Which of the following statements about the sleds are true? There could be more than one choice. Well, this is the same question I just encountered with the cars. I know that it's mass independent, but this is a multiple select, so there could be multiple positive answers. I'm going to be careful here. The friction from the snow will do more negative work on the heavy sled than the light sled. Well, yeah, because the heavy sled is moving at the same speed as the light sled, so the heavy sled has more kinetic energy, so it's going to take more negative work to stop it. The heavy sled will slide farther. No, we know they're going to slide the same distance. The light sled will slide farther. No, we know they're going to slide the same distance. The friction from the snow will do the same amount of work on both sleds. Nope, it takes more work to stop the heavy sled. Both sleds will slide the same distance. We verified that in a previous problem. A heavy dart and a light dart are launched horizontally on a frictionless table by identical springs. This is the only spring question in the assignment. Both springs are initially compressed by the same amount. Identical springs compressed by the same amount. That means these darts are launched with the same energy, because the initial energy is the energy stored in the spring. The final energy is the kinetic energy of the dart. The spring energy of the spring is transformed into kinetic energy in the dart. So the darts will have the same energy. Which of the following statements about the darts is correct? There could be more than one. The lighter dart leaves the spring moving faster than the heavy dart. Well, they have the same kinetic energy. So to have the same kinetic energy, the lighter dart must be moving faster than the heavier dart, so that they'll have the same kinetic energy. The spring that launched the heavy dart had more initial, nope, they had the same initial potential energy, because they're identical springs compressed by the same amount. The spring energy is 1/2 kx squared. So it depends on the spring constant, they're identical springs, and how far you compress it, x squared. So they have the same spring energy. The darts have the same kinetic energy just as they move. Oh, wait a second, I didn't want to select that. I'm selecting ones that are true. The darts have the same kinetic energy just as they move free of the spring. Yeah, as I said, because the springs have the same kinetic energy, the darts will have the same kinetic energy. Did I say that right? Because the springs have the same spring energy, the darts will have the same kinetic energy. Both springs launching the darts had the same initial elastic potential energy. Yes, I've been saying that over and over again. Both darts move free of the spring with the same speed. No, they must have different speeds because they have different masses and the same kinetic energy. Question 19 submitted. Look at that. I got them all right. And if I study my notes and the problem solving that I did, maybe read a little bit more about the conservation of energy, I should be good to go for assessment 5.